Hey guys, how's it going? So the contest last night did not go very well. I was expecting I would be able to solve C, but I could not because I was not that prepared for inclusion and exclusion questions. So today we are going to try up solving D. Alright, so we'll try D now. I did C this morning and I tried it again. It was not that hard. It was a very simple inclusion exclusion problem. So this is going to be slightly harder. Let's see. So there's linear strip divided into m cells, numbered 1 to m from left to right. You are given n segments. Each segment is defined by 4 numbers, left, right, and p, q. So the segment covers cells from left to right inclusively and exists with probability p by q independently. Well, let's see what that means. Calculate the probability that each cell is covered by exactly one segment. So there is, I believe, the statement is trying to say there is not supposed to be any overlaps. Let's see the first test case and find out. So we have n and m, and we have n segments, and the linear strip has m cells. The probability that each cell is covered by exactly one segment, take a modulo of this number. Alright. Formally, the probability can be expressed as an irreducible fraction x by y. You have to print the value of x, y inverse mod this, and y inverse is an integer such that y dot y times y inverse mod this is 1. Okay. Now so let's see this one. So n is 3 and m is also 3. So we have a linear strip with 3 cells, and we also have 3 segments. Now what does the question say? The segment covers the left and right and is supposed to exist with a probability p by q. So let's see. The first segment is from 1 2. Okay. Now the first segment right here. It's our first segment. I'll just color this instead. And this is supposed to exist with the probability of 1 by 3. Okay. Then we have 3 3, this right here, is supposed to exist with a probability of what? 1 by 2 and 1 3. So it would be this right here. 1 2 3. It's entirely is supposed to exist with. What is the question even asking? I don't get it. I don't understand. Uh, you are. Probability that each cell is covered is by exactly one segment. So either a segment exists or either the segment does not exist, and the probability of that segment to exist is this right here that we mentioned here. That is the case, then this is supposed to be something like the probability for only one segment here is that either we have this and we don't have this, so in that case we 1 by 3 into 1 by 3 plus, and since it's not all right, I get it. So so the question is asking that we can only have a single segment here, and there's a probability for the segment to exist, and so we can also have a probability of that segment to not exist. And if there is an overlap, we will if there is an overlap, we will exclude other segments and only include one segment. So this can be, I don't know, 2 by 3 as well. I'm not sure, but the question does not say this. Question say the probability is 5 by 18, and I think we can get that by saying that 1 by 3, and then we exclude this right here, so this becomes 1 by 3 again. Then we add to this right here. The probability for this is 1 by 2 times 1 by 3. So it becomes 1 by 9 plus 1 by 6, which becomes 2 plus 3 by 18, which is 5 by 18. And similarly, let's say that we include the red segment, which is overlapping all of them. If that is the case, so it becomes 2 by 3 times 2 by 3 times. We're going to exclude this, so that becomes 2 by 3 again. I'm going to add 2 by 3. So we can say that we can just take this as a and multiply it by multiply it as a whole with all the overlapping cells. We'll come to the overlapping cell. We will say, all right, we can exclude this. All okay, we can exclude that. So if we exclude it, it becomes 2 by 3. Then we will continue the exclusion. Right. And then we can plus 1 by 2 if I'm not wrong. This will become 2 by 3 times it becomes 4 by 6 plus this is not working. This won't work. I don't know how, but yes, it is not going to work out. Okay, let's try again. Let's try. M segments. We have 3 segments. We need to remove. Oh, let's try the question again. Let's try this again. This is 2 by 3. We can also come here. This right here was 1 by 3, and this right here is 1 by 2. Either it becomes 2 by 3 into 2 by 3 plus 1 by 2, or it becomes 1 by 3 into, sorry, it becomes 1 by 3 into 1 by 3 plus 1 by 2. This becomes 5 by 18. This becomes we can just look up a bit of test cases and see if we can make sense. There is no solution for this one. I guess we can just.
So I will be very grateful to have a conversation with you. So just DM us or call us after this contest. Okay, so let's meet in the on the chat. So just DM us or call us after this contest. Okay, so let's meet in the on the chat. So hello everyone. I'm back with the another exciting new of college project, major minor project, or full stack project, or if you want to build any type of website for anything, any purpose. See, and we have completed more than 30 projects. So if you
He's not talking about any solutions right now, right? We will wait for the solution of this one. Until then, we can, I guess, solve few more CP31 problems. Let's start easy. Let's start with 1200 rated problem. Once upon a time, I decided to come up with an outstanding problem for some stage of ROI. One of them gave us the problem prototype, but another stole the idea and proposed that problem for another stage of the same Olympiad. Since then, the first Mike has been waiting for an opportunity to propose the original idea for some other contest. Mike waited until this moment. You are given an array of n integers. You are also given q queries of two types. Replace ith element in the array with integer x. Replace each element in the array with integer x. Okay. After performing each query, you have to calculate the sum of all elements in the array. So we can either swap one element or we can just swap it the x within the whole array, right? Give me a second. So All right. So all right, all right. So we have 5 elements. Then we have 5 queries. First, he tells us to replace the element at 1 with 5. So the sum becomes 5 and 4, 9, 9 and 3 is 12, 12 and 12 and 2, 14, and then we have 5 here, so it becomes 19. And he tells us to replace all of that with 10, right? So 10 fives are 50, okay. Then he tells us we're going to replace what is at 5th index with 11, so it becomes 51, I guess. Then he tells us to replace what is at 4 with 1, so we are losing like, I know, 10, so it's going to be 40. I don't know, it's going to be 40 or 41 or 42, alright, makes sense. Then he replaces all that with 1, so we get a 5. Okay, the problem is pretty straightforward. Problem is quite straightforward. Looks like more of a data structures problem to me. What we can do is keep track of so what is the size of n? So n is 10 to the power 5, so we can do at best n log n. Okay. Let's just store the sums. Then when the operation happens, we can just add it. That looks pretty straightforward. We can just increment the sum but with the difference, so it will be 5 minus 1, 4, and we will add 4 into the sum of 1, 2, 3, 4, 5. That will give us the answer for the first query. So that would be 5 and 4, 9, 9 and 3, 12, 2, 14, and 1, 15. So 15, and then we add 5 minus 1 to it, so it becomes 15 plus 4, which is 19. Okay, looks very straightforward. Right. So let's just int n. let's say that the second operation happened right here. Okay. Oh, and okay, okay. So we keep track of the sums. Then when the second operation happens, we keep track of whether we keep track that, all right, if the second operation happens, dude, I get this now. Now I get it. So how do we keep track of the second operation and the swaps that happen after the second operation? How do we keep track in of 1 or log of n, right? That is the problem. Let's see, 1 2 3 4 5, 1 2 3 4 5, and let's just go through it again. What is that? 1 gets replaced with 5, the sum becomes 19. Now what happens is we tell that everything turns into 10, so everything is now 10. It's all supposed to be 10. So after that, what is that? 5 gets replaced with 11, so this gets replaced with 11, right? And now we need to remember, that after we did this operation right here, we replaced this with this. Or do we have to remember? We have to remember, because let's say this gets replaced with 9, the sum is supposed to reduce by 9 minus 11. So it's going to be sum plus equal to 9 minus 11, so it's going to reduce by 2. Now how do we keep a record of this? One thing would be to keep track of, okay, I We can say all have swept. Oh, no, no, we can't say that. Hmm. Do you have any other guides? Okay, so I get an idea. I have an idea. We can keep track of the last reset. All right. When at what step was the last reset? All right. Last time. At what query? So we can say query number. And then we can assign a value to that, and also have something called last reset, which will assign the we will assign the value of the last time the last time the entire array was reset, right? It will store the query number for that. So we can say something. We can say it's changed. And then we can say int last reset was at 0. Then we can say for int I is equal to 1, I less equal to 0, I plus plus, and basically let's just say for int query capability. If t is 1, we're going to take inputs of we're going to check if what is at I. So we can say modified at I is greater than so the version the query number at which we updated the we did the first operation is greater than the query number at which we perform the reset operation. So we can say reset. Okay, then what we do sum plus equal to we can say x minus a of I, and we can also say a of I becomes x. Else what happens last reset. So the other case is that okay, so we can initialize um, we can say that else what we do, we sum plus equal to x minus. Okay. Else what happens? Else we if t is equal to true, we take x as input and we say that and we can say that the value is a of I. Do something like this. We can say int val is equal to 5 of I is greater than last reset. Is it true? Then we do this. So sum is going to be equal to x minus value and then a of I is equal to x. Then we can say that take input of x. We can say last reset. Okay. First question is giving us the wrong answer. Why? Hmm. Okay, 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 I get it. Forgot to do this. Wow, I got a wrong answer. If we forget some edge case. Do we have an overflow? Like an overflow to me. So it could be this. It could be that accumulator is not working properly. So we can say sum is equal to 0 or I. Looks like an overflow to me. Accumulate can't handle those numbers, so I guess that's the reason. Now the output is correct this time. Where did we go wrong? This again is an overflow. Maybe it's an overflow. I'm pretty sure it's an overflow. How do we do this now? Like, these are in longs though, so it should work. And an iterator should also work with long, so it should not have been a problem. Let's just try. Is there any other place that we are using something weird? I'm pretty sure. So if I get it wrong this time, it means we have a problem with implementation. We are making some silly mistake. Okay, we are making some silly mistake. So I will just look at the solution now. I was doing the same stuff. क्या हो यार
you also want to just want to build any type of college project, major minor project, or full stack project, or if you want to build any type of website for
All right, let's try one more. Try 1300. Or should we do this? I think let's try a harder one. We'll do this and then we'll do it. So you choose a pair. You are given an array A of n positive integers. You perform the following operation on it. Choose a pair of elements. Choose one of the divisors of the integer ai. Okay. Replace ai with ai by x and aj with aj times x. Okay. Determine whether it is possible to make all the elements in the array the same by applying the operation a certain number of times, possibly 0. For example, let's consider the array 100, 2, 50, 10, and 1 with type elements perform 2 operations on it. So looks like a very number theory problem to me. We can just build prime factors of each of these elements. Alright, I'm back. So we can make an array same by, let's say, so let me show you 100 to 50 10 1. So let's see, 100 to 50 10 and 1. So the prime factors are 2 into that is 2 into 2 into 5 into 5. This is 2. This is 2 into 5 into 5. This is 2 into 5. This is 1. This is nothing. All right. And we need to find something. So see, this is here. So we need to find we can count the number of 2's, which is what? Which is 1 2 3 4 5 5 2. Then we have 1 2. Number of 5's are also 1 5. Since these prime factors are divisible by 5 itself, by n, so this is 0. So this is possible. So we have 10 to the power 6, and we can store factors count, I believe. Then if we have the factors, we can just sum those factors, I believe, and at the end iterate and check if number of factors of each of them are divisible by n. If that is the case, so it is possible. We will store a map of each number, and I will say that we have a map of each number, and you can store counts of that number and a prime factor, right? And we will iterate through this and build the final array of the counts of the prime factors. and then we can say, we can check if all of them are even, or if all of them are divisible by n. If that is the case, then this is possible, otherwise it's not. Can we simplify this problem? I don't think so. We can't do that. So 1e6 is going to be sorry. We can say that so at worst 2 to the power n is equal to 1e6 or something like that. Then ln of n ln of 2 is equal to ln of 1e6. N is equal to ln of 1e6 divided by. So this would be ln of 1e6. Can I write that? To the power 6. So at most we will have 20 prime factors. So this will be O of what? O of 20n. So it doesn't make sense. Doesn't make a difference. It stays O of n. We will build our primes forwards. So build calls and do something, and we also need 6 plus 1. We also need map of 8 of n, count of n. So we have an array of maps, and we say that, and we will say for in I is equal to I less than we can use size of map. We can say if count of I dot size is equal to 0, or int j is equal to I times 2, j is less than n, j is plus equal to int x. What it is saying? It is saying to close it because so now we are going to x j. I'm going to say prime count of j a prime count of j, and the prime factor is I. Going to get incremented. So in x equal to j, sorry, it's going to be if j percentage I j percentage I times I. So we divide j by I, and then we check is it divisible by I again. I'm doing some very weird shit right now, but this looks interesting to me. So prime count of j of I plus equal to prime count of j slash I. Right. It feels so weird, man. It doesn't feel right. prime count gets incremented. Okay, now what we do? Now we have a for loop, then we have any statement, then we have for loop again, then we have while loop is right. So we need this, and then we can build counts, and then we will say vector. Let's just do map of int and then we say we're going to iterate through all the prime factors, and we're going to say prime factors of x dot first is going to be incremented with plus equal to prime so our prime factor is getting incremented by x dot second, right? And then at the end of the iteration, we're going to iterate to the map again. So say on or prime vectors. We are going to say if x dot second percentage n is not equal to 0, return else. What do? We do 1 and we change. But then it's very wrong, very long. Shift plus this was very intuitive for me. Because I have practiced in this problem. I believe this is the right way to solve this, unless I get a TLE, which is very likely right now. Okay, we did it. We did this, which is very surprising to me. First try. It's a very interesting problem. It was really fun doing this one. It was fun because I knew how to do this. I think the good thing was that within 5 minutes of reading the problem, I knew what to do straight away. So something that I was very surprised. In the last problem was very trivial for me. we had to do something like a sort of a version control basically to implement the last problem we to solve. And similarly, I had trouble with that array problem that I did a while ago, which was this one right here. Romantic glasses was hard one because I did not perceive the elements to just subtract from the array. So this is something very interesting. You're given an array A of size n. You will do the following process to calculate your penalty. Split array A into two possibly empty subsequences. Okay, we are going to split in and such that every element A or every element of A is either in S or T. Split array A into two possibly empty subsequences. Okay, we split them, and then we say that I need a break now. I feel like doing this problem. So we'll take a break, I guess. Take a longer break now. I need to take a bath as well. I can probably like 10-15 minutes. All right. You are given an array A of size n. You will do the following process to calculate your penalty. Split array A into two subsequences S and T such that every element of A is either in S or T. Okay, we are going to divide them. For any array B of size M, define the penalty of B of an array B as the number of indices between 1 and M minus 1, where Bi is smaller than Bi plus 1. Okay, so that is the penalty. The penalty is the number of elements in which the next element is greater than the previous element. Number of occurrences of that. Total penalty is PS plus PT. So we need to minimize the penalty. Why is this invalid? I need to delete something. Alright. So 1, 2, 3, 4, 5. I have to split this such that the penalty is minimum. We can split it from here. We get what? We get penalty of penalty of 2 and 3, 3 and 4, 4 and 5. We can actually build a subsequence, right? So it can be 1, then we can have 3, and then we have 5, and then we can have 2 and 4. So it won't make sense. In every possible way, this is going to make an increasing array. So our goal should be to make the array as decreasing as possible, which means that if we choose one element to be part of the array, we have to look for something that's larger than 1, right? Something that's not decreasing. So we can look at we can look at 1. We can say, all right, let's go to 2. 2 is greater than 1. We don't want that. 3 is greater than 1. We don't want that. 4 is greater than 1. We don't want that. 5 is greater than 1. We don't want that. And you end up happening is you get something that's worth 3, right? So similarly, we start with 8. There's nothing greater than 8. Sorry, there is a lot of stuff that is smaller than 8, so we can do something like 8 and 2, and then we can see, all right. If let's say we need to have both arrays decreasing, right? So now it should be something like we can have 8 and 1, and then we can have 2 either here or here. Let's just have it here. Something like that. But how do we do this, man? How do we do this? We can check like this, right? The problem is, I know this is a DP problem because I have seen the tags already, but I can make sense of how to approach this as a DP problem. So I don't know what to do now. We can greedily try we can greedily try all of these combinations, and if we have any sort of way to check the score, is there any way we can check that? I don't know. So any number that is smaller than this, we accept that, or what should be the greedy approach? Like how to implement this greedily. So let's say if I have something like a large number, then I get small, and then if we move over and have another large number, this causes our penalty to increase, right? So let's say a, then I do a 1. So it's going to have a penalty of 0. The other one is going to have is 2, 1. So it's going to be 3, 1, 7, 4, 3. This is one penalty right here. 7 and 4. So this is one penalty right here, right? What else do we have to check? Let's build another test case. Let's say that I have 3, 5, yeah, 3, then we have so we'll start with 3. We'll see 3, then we go to 2, and then we go to 1. 3, and then 2, 1. So the remaining stuff is 5 and 4, respectively 5. What else is possible? I don't know. I don't think this is the right approach, but let's see. If AFI is smaller than previous, then we get previous is equal to AFI, else so that is we are missing a certain test case. I am very certain that we are missing that test case. So let's just try to think about some weird test cases that might actually fail when we have a penalty of 0 in one subarray and we don't have the minimum possible penalty in the second subarray. So let's say I am integers a, b, c, d, e, whatever. Now it is possible that I keep this. I don't know. I don't get it. How can is there any other edge case? There has to be some sort of edge case or some sort of general case that I am missing because the 300 problem is not supposed to be this easy. This is like an 800 problem, dude. The solution is not right. I'm pretty sure. So when we build a subarray, we keep a large number here, we keep a smaller number here, we keep a smaller number here. And the rest of the numbers go to the second array. However, God. Second array is supposed to second array is supposed to have whatever is left behind. But what if we have to try keeping both decreasing instead of only one array decreasing? Does this make any difference? So let's see that. Let's say let's come back to this test case. Let's say that let's say we keep this number. What if this was something like 8, 2, then we have 5, we have 1, 1, 7, 4, 3, right? So if we keep this, then this goes here. Whatever. I don't know. Let's just run it through and let's just check it. I can come with any test case that fail. Let's just run this. One, two, three, 4, 5, 6, 7, 8, 9. The answer should be 0 if I'm not wrong. The answer is 0, but yeah. So 1, 2, 2. Why are we failing this game? 1, 2, 2. This should actually work with my test case. With my implementation, this should work actually. So start from here. Push these to the second array. Oh, what are we doing? What are we doing? the segment keys selected. I don't know how to work the segment keys. One, two, three, four, five, six, seven. Let's start.
This is Hello 2024 of Code Forces. We're gonna solve the third problem, that is grouping increases. So grouping only increases here, but our rating does not increase, but no problem. Let's keep practicing. So we have an array A of size n. So let's take a sample array like 1, 2, 3, 4, 5, and you'll do the following process to calculate your penalty. Split the array A into two subsequences S and T. Subsequence means what? You can select those numbers in the same order by removing certain elements. So 135 I'm taking, and balance is 24. You should put in T. So whatever number you take, it should be either part of S or either part of T subsequence. After this is done, they are telling for an array of size M, define the penalty as an array B as the number of indices I between 1 and m minus 1. That is, when bi is less than bi plus 1, we can say that there is a subsequence is possible. To make it clear, let's take this 5, 4, 3, 30. So 5 is greater than 4 is greater than 3. So the penalty is 0 here, 0 here. Only for this the penalty is 1. So total penalty is 1 here. So let's understand this with the help of an example so that it will be more clear. So 1, 2, 3, 4, 5 is here. So for 1, 2, 3, 4, 5, they took 2, 4, 5 in one array, 1, 3 in different array. 2, 4, 5, the penalty is 2 less than 4 less than 5. Penalty is 2, penalty is 1, total is 3. For 8, 3, 1 they took here, and 2, 1, 1, 7, 2, 1, 7, 4, 3 they took here. For 8, 3, 1, it is a decreasing sequence, right? So the penalty is what? It is 0, because there is no number where the left number is less than right number. The consecutive numbers are not there. Here only 1, 7 is here. That's why the penalty is 1. 1 is less than 7. Others are all decreasing. So 1. Now, by seeing this, what did we observe? We will think that, okay, we'll put all the decreasing numbers in one array and increasing numbers in other array. So decreasing numbers, how do we optimally choose it? We'll think that, okay, let's take the longest decreasing sequence that is possible, and the balanced numbers that are left out, we can put it to other array and calculate. But how did we derive this longest decreasing sequences? There is already an algorithm for longest increasing sequence where you recurse and memorize or do tabulation approach. It's like a DP problem. The standard way is it's like a n square algorithm. But the problem is the n value here is 2 into 10 power 5. So definitely the n square value won't work at all. N square can maximum work till 10 cube or at max at 10 power 4 also. But here it won't work. So we have to optimize that complexity further so that longest decreasing subsequence is not going to work. That algorithm not going to work. So that may or may not work, but we'll get TLE for sure. What is one thing we can do is we have to classify these numbers number already inside. And in order to make our algorithm standardized, I can say that SL is less than TL. Okay, so this is our assumption. See, it may happen that SL is greater than TL, but our only goal is one of them should be less. So if SL is greater than TL, I'm automatically assuming that T comes first and S comes second. If this is there, I am putting it here. So how do we solve in the coding way is, I can just swap these numbers, right? SL and TL. I'll just tell you. So the for now, SL is the
All right. Let's get back to it. So, consider the following approach. We start with empty arrays B and C, then insert elements of the array A one by one to the back of B or C. Our penalty function only depends on adjacent elements. So at any point in time, we only care about the value of the last element of the arrays B and C. All right, makes sense. Suppose we already inserted A1, A2, dot 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 AI minus 1 into arrays B and C, and now we want to insert AI. Let X and Y be the last elements of array B and C respectively. If they are empty, use infinity. All right. Note that swapping arrays B and C does not matter. So, without loss of generality, assume that X is less than equal to Y. So what they're saying is we are building two arrays, all right. B and C. They are built using the array A itself, all right. And the last element here is X, the last element here is Y. So they're saying that we assume X is less than equal to Y. It's a weird assumption. So this might be something like this might be a case where we are inserting large elements in Y and smaller elements in B. Large elements in C, smaller elements in B. Okay, that's all right. Let's just move ahead. So if A of I is smaller than or equal to X, this means we are in trouble, right? We are in trouble because wherever we place them, wherever we place this number is going to actually we're good. We are wherever we place this, we'll be fine because So, a of I is smaller than or equal to x. If that is the case, this means that wherever we place this number, if we place this in front of B or we place this right here at C, in both cases the penalty is 0, because if x is greater than ai, y will also be greater than ai. So we are seeing something that is non-decreasing, right? We are seeing something that is non-decreasing, or maybe something that is equal. If that is the case, this means the penalty is 0, right? The editorial says that we inserted at B. Let's see the reasons later. So if y is smaller than ai, insert ai to the back of the array with the smaller last element. So again, makes sense. We just put it right here in B. If x is less than ai is less than or equal to y, insert ai to the back of the array with the bigger last element. So this is something that is confusing. This is something that is confusing. So x is less than ai is less than or equal to y. This means ai is in between x and y. In that case, we're inserting it at y instead of x. Why? Because in this case, if we insert it at b, if this gets inserted at b, it's going to cause us problems, because this becomes an increasing sequence right here. This becomes larger than x, and this will cost us some penalty. All right. So the greedy algorithm was pretty simple. I failed to understand it. How were we supposed to then interpret this question? The proof of why the greedy approach is optimal is given below. If ai is smaller than or equal to x, in this case ai is not greater than the last element of the both arrays, so inserting ai to the back of either array will not add additional penalties. However, it is better to insert ai into the array with the smaller last element, so that in the future we can insert a wider range of values into the new array without additional penalty. That's very interesting, very interesting. And I did not think about it this way. So what they're saying is that this is also, I thought about this for a second when I was attempting this question, that how am I going to make sure, how am I going to preserve the larger values and whatnot. So this makes a lot more sense. This makes a lot of sense. So the idea is that if we insert a number, ai is smaller than or equal to x, right? in this scenario, if we insert this here, the penalty remains 0, but the next number that we're going to insert should be smaller than AI, right? Smaller than AI, right? So a of I plus 1 is supposed to be smaller than or equal to ai to be inserted into b back again. So what really is happening is that we are going to a smaller and smaller number, and eventually adding a number in this array is going to be very hard. Adding a number that is not smaller is going to be very hard, right? And if we keep y large enough, we will have a large range of values to insert, to keep inserting without costing us penalty. This is very interesting. Y is smaller than AI. In this case, AI is greater than the last element of both arrays. So inserting AI to the back of either array will contribute to one additional penalty. So let's say that AI is greater than both X and Y, right? In that case, it doesn't make a difference if we insert it in first or second. So look, listen, if we insert that element in B, so the last element of B, which is the last element of B, which is X itself, is going to be greater than Y in the next iteration. What does that mean? That means we have a greater range of values that we can work with, that we can then we have a greater chance of adding stuff without costing us penalties. So that is pretty cool. That is something I never thought about. That's really smart. So the fundamental idea here was to right, so the fundamental idea here is that we want to insert elements into the array such that either the element we are inserting is smaller than the previous element, smaller than or equal to the previous element in that subarray, or the element we are inserting is greater than either of the elements in the subarray. If it is greater than either of the elements in the subarray, we will insert the greater element in the smaller array, right? So at a given point, if any array is smaller, we will insert it into that, because we want to have maximum possible range of values, and it won't cost us that much penalty then. So in each iteration, we will check the array which is smaller, which has a smaller value, and use that, and then use that kind of array. So we use that array for operation basically. So So what we can do is basically, let's just keep x and y as it is and assume them to be x is less than or equal to y. And if at any point x becomes greater than y, we just swap them. We just swap them. And then it becomes very easy. Then it becomes very straightforward. Then we can just check if AI is smaller than x, and then we can also check if it's between x and y, and we can then also check if it is greater than either of them. And if that is the case, then we assign x the AI value. Let's do this. Let's do this. So my previous approach was just build a decreasing list and just pray to God that the second list we are building somehow has the least possible penalty, right? I was somewhat right, but it was just stupid. The approach was simply stupid. So if I were to solve this again, how would I had come up with this particular intuition? So let's try to reread the problem. Let's see. Where did it go? I'm thinking about doing one more 1400 before we log off. It's not going to be the best thing to do right now because I have a lot of work to do as well. But I will try to solve 5 problems today. I will see. So I had to assume that we start with, I had to think about it this way. Start with 2 subarrays S and T. Then we start with the first element of the array A. We go to array A, we look at the first element, and we insert it. We insert it at X, I guess. So we have to decide how to insert this here or here such that the penalty is least, right? So X, so it would have looked something like this. Then we would have said that. So the first thing to make sense was we need to keep track of the last elements of both the subarrays, and then we have to know that, okay, so if I insert this element here, what will happen? Will I get a penalty or no? So if I insert here, I get a penalty, yes or no? Will I get a penalty here, yes or no? And the thing about subarrays was that I had to only iterate through them from first till last, and we had to insert these into subarrays in that particular order, right? We can't go anywhere around this because the question mentioned we are talking about a subsequence actually. No, we are not talking about a subarray. So that was something to keep a note of. This was a subsequence, not a subarray. And then I had to decide that first thing was to make sense of this. right here. Then the second thing was to understand that I had to insert them to minimize the penalty and how the penalty worked. That was the second thing to understand. Then the third thing to understand was the case where my AI is greater than either of these elements, right? It's greater than either of them. So what would I do in that scenario? And then I needed this understanding that the goal is to minimize penalty, and if we have x and y as large as possible, right? We want x and y both to be as large as possible, so that whatever element we insert is going to not cost us some penalty, right? If x kept decreasing and decreasing and decreasing, at the end it's going to cost us a penalty, because eventually we might get a number that is bigger than x, and that has to get inserted somewhere, right? So I would say this was a weird problem. These array problems, I think this is my third array problem and I'm struggling with this, so I need to particularly practice this. I can do that, I guess, because there is no certain tag for these sort of problems. Codeforces doesn't have that. Anyways, let's start implementing. So the value of AI has to be smaller than or equal to n. Let's just 1 to e5 plus 1. So what we see is we see if x gets greater than y, we just swap them. And then we see if a of I is smaller than or equal to x, then x is equal to a of I. A of I is greater than x, and n smaller than equal to, and a of I is smaller than equal to y, then y becomes a of I. And else what happens? We also have to increment the answer. Getting to the point that making an assumption that x is going to be smaller than equal to y is something that I find hard to understand, hard to think about intuitively, I guess. I have to think about it. How do we get there when I am solving this problem again? Okay. So should we do this or try to absolve? Let's try to absolve actually. Let's go to contests, and that was really a huge change because that contest had a very interesting 1400 problem that was somehow able to solve, which was something that I found really surprising. So that was my biggest rating change, I guess, after probably, yeah, that was my biggest change. Kind of suffered in this one, so let's see. Or maybe let's try another problem. I will wait for the editorial if we get some hints or something. So Polycarp is designing a level for a game. The level consists of n segments on the number line, where the ith segment starts at the point with coordinate li and ends at the point with coordinate ri. So a level consists of n segments on the number line, where the ith segment starts the point with coordinate li and ends at the point with the coordinate ri. The player starts the level at the point with coordinate 0. One move, they can move to any point that is within a distance of no more than, okay, After their ith move, the player must land within the ith segment that is at coordinate x such that li is less than equal to x is less than equal to ri. This means okay, that's a lot. That's a lot of information. So in one move, they can move to any point that is within a distance of no more than k. Alright. After ith move, the player must land within the ith segment. After the first move, they must be inside the first segment. After the second move, they must be inside the second segment. After the nth move, they must be inside the nth segment. The level is considered completed if the player reaches the nth segment, following the rules described above. After some thought, Polycarp realized that it is impossible to complete the level with some values of k. Polycarp does not want the level to be too easy, so he asks you to determine the minimum integer k with which it is possible to complete the level. So the segments may intersect, which is something to keep note of. Let's see, we have 5 segments now. So we start from 1, 2, 3, 4, 5, right? 1, 2. So the first segment starts from here till here. The second segment starts from here till here. All right, and the third is from, I'm sorry, what? Okay. It's not supposed to be this way. It's going to be 5 segments. Okay. 1 to 5. There's one segment right here. Then we have 3 to 4. 3 to 4. That is our second segment right here. This is our first segment. This is our second segment. And third segment is 5 and 5 to 6. So 5 to 6, that is our third segment. And then we have 8 till 10, 8 till 10, 6 dot dot 8 10. That is our fourth segment right here. We have some missing, we have some levels here which don't have any segment at all. So 8 till 10. And then we have 0 and 1, which is something weird. It's really weird. So 0 and 1 is fifth segment. What is even that? Uh, All right. So we can move back and forth. We can move back and forth, and we need to get back from the fourth segment back to fifth segment, which is right here. Let's get back to it. So we'll make a jump here from 8 till here, 8 till 1. So we can get back to the fifth segment. We need to find the minimum integer k. So to get to the first segment, we need to have a minimum jump of 1. Okay. And then to get to the second segment from the first segment, we need to make a minimum jump of 2. So we start with this from 0, 0, and we tell ourselves, all right, we can get to the next segment in 0 moves. And then we check it. Can we go to the next segment in 0 moves? No, we can't. So how many moves do we need? We need 1 move. All right. Change our k to 1. And then we tell ourselves, all right, now let's say that I am playing very smartly, and once I reach here, how long of a jump do I need to make? Get to 3, get to the second segment. So check if we are only 1 block away from here. We are not, so we must have k is equal to make the next jump. And then we come here at 3, and then we tell ourselves, all right, can we make it to 5 with k is equal to 2? Yes, we can. So we make a jump, we are good. Then we say, can we make it to 8 with k is with 5, right? So we realize that we can make this jump, right? We can make this jump with k is equal to 2. So k is equal to 3 it is. Then we make a move with k equal to 3, move to 8, and then we tell ourselves, all right, now can we make a jump back from 8 till the fifth segment? Can we make that? So the minimum distance right here is 8 and 1, which is 7. So we can make it with k is equal to 3. We need to make k is equal to 7 to make this jump right here. So that is how we get it. Now I'm thinking about this test case. Let's say So right now the approach we are working with is start here. We have to make it to the bare minimum. That's it, right? We just need to make it to the bare minimum. And if we make it to the bare minimum, check, can we make it to the bare minimum, the next one with this? If we can, it's all right. We can do that. If we slightly overshoot, if we slightly overshoot but are still within the range of k, so we'll make that jump. Why? Because now we can move further from here, right? But let's say the next segment was here. In this case, it would be optimal for us to make the jump to the bare minimum so that we can have greater distance in this direction and we can jump here, right? And then if the next segment is on the right side, we can say, all right, now let's make a very good jump. Let's make the best jump we can and get here with the least possible value, obviously. So that is something, okay, so that is something really interesting. Let's say that we have very small numbers right here, okay? And then suddenly we have some very large number. So make a jump to the to make the bare minimum, or do we have to make a jump from bare minimum? So by bare minimum, I mean that let's say we have a value of k, and then we have to travel and the distance that we have to travel, right? So there are three cases. The first case is that distance is smaller than k. Okay. Second case is the distance is equal to k. And the third case is the distance is greater than k, right? So if the distance is smaller than k, we have a lot of free will. We can make a jump from the start. Let's call this the start. So we are starting from here, and we have a large value of k. So this is our range of jumping. Let's say I'm a frog and I can jump this far, and I want to land here, right? So I'll say that I'll ask myself, okay, I will land here, but where do I go next from here? If I go to the right, if I have to go to the right after this, so it would be best for me to jump as far as I can, which is the minimum of k and the right of that segment. So we can land as close to this end right here because we're going to make a jump forward, and that will make much more sense, right? And if we are moving left, then I will just jump to just barely make it to the left. Okay. And similarly, let's say the distance is equal to k. What do we do then? So the idea is that let's say this is what I was thinking initially. I was thinking that let's say we make it to this end right here, right? And somehow, to make it to the next segment, right, we fall one digit short. But if we had that made that jump just one step ahead, right, we could have landed in the next segment. So if we have made the first jump is the maximum possible jump, and yet we still fall short of making it to the next segment, this means that whatever we do, we have to change the key. We can just simply not make it without this. All right. So this is a very greedy problem. And so distance is less than k is the ideal solution for us. Distance is equal to k. Again, we can't do much. We'll just make the jump to wherever we're landing, right? And then again, if distance is greater than k, we are going to make the bare minimum. And after making that bare minimum to the next segment, and yet we are still not able to make a jump into the next segment, we are going to then again increment k. So this is something that might work. I don't see any problem with this. I was thinking, what if I had to decide a certain value of k in case that distance was greater than k, but it doesn't make sense to determine this a certain value of k that might be ideal to make the next jump as well, right? I don't know if I am wording this correctly, but in my head it's starting to make sense. So you can keep track of a boolean that tells us we don't even need a boolean. We can just decide for this case. All right. So So we can call this an array of segments, and n plus 1. Then we will do for in I equals 0, I less than n, I plus plus. You don't need one based indexing. Segment. So we're gonna say boolean right is equal to true. Then we say for int I is equal to 0, I less than minus 1, I plus plus. First we are going to determine the direction of the next step we are going to make, right? So we have to always be 4 steps ahead. So we will say that if and now this also has some edge cases. So the first thing we need to determine is let's say this segment is within our current segment. We need to make a bare minimum. If the current segment is greater than, if the current segment is before this, so we have right is equal to true. Look, I mean, it's something like this, right? We are here and we need to move right. So if we need to move right, do we have to make the bare minimum, or do we have to try to push ourselves to at least make it closer to the next stop? So we will say that, all right, we have to move right after this, right? If we make it to the bare minimum, we will have to move right. So this is interesting. How do we work with overlaps? How can I work with overlaps? Okay, we will see that, but first we are starting here. We have to decide how long of a jump do we make to this segment, and we know that the next move we are going to make is to the right. Okay, so if we know that we're going to make a move to the right, then we're going to try our very best to make a very long jump. And if we know we are going to go to left after this move, then we are going to make the bare minimum. I'm also thinking about this case. So let's say that I have the ability to land anywhere I want. I can land here, I can land here, alright. So where do I land? Here's the thing. I have to move right from here. That is all I need to know. Because if I am able to make it here, right? I also have the ability to just come here and then go there. Not much of an issue. This is not something to worry about. In this case, we are not going to try our very best. We're going to just make the bare minimum. We're going to make a bare minimum, and then we will see how to get from there. So this will be for right is equal to false. This will work. Let's say we are in the other direction. Let's say we have to make a move left. What do we do then? We start here, we are somewhere here, we have to go to the left. So we need to know where are we going again. So we are going to go, if we're going to go further, we have to also make our very best in this direction as well. That is something that I just forgot to mention, that I forgot to take account of, that we need a lot of direction actually. So we are actually going to need to know what is going to be the direction of our current jump and what will be the direction of our next jump. And if the direction of the jumps is same, we will try our very, very best. And if we have to I'm sorry for the noise. So we need to keep track of both directions. And this is something very interesting. So we will see if the current direction is left or the current direction is right, and then we'll also check what will be our next direction. Is our next direction going to be right, or is our next direction going to be left? So if our next direction is going to be left and our current direction is also going to be left, then then we do it in a totally opposite manner. So this is really confusing. Then we are going to make a jump from the current position so the distance is actually going to be negative as well, and since the distance is going to be negative, we can this is going to be a very lengthy code. How will we know the next direction of our jump before we even make the decision, right? So how do we know that? Again, we are just concerned about the overlaps, right? Yep, we are concerned about the overlaps. That's pretty much it. That's pretty much the problem. So if there is no overlap like this, we will be fine with what we were doing. And let's say that there was an overlap. If there is an overlap, we make the bare minimum. Is that true? Yes, it is. When will we make the bare minimum? When we make bare minimum when directions are not same. Directions are not same. This means overlap does not have same directions. The same thing we talked about previously, but in the opposite direction. So overlap will be considered to not have the same direction, right? And how do we know that, say, whether we are going in the same direction or not? So we will say that this is left, this is right, this is left, this is right. So the current direction can be determined pretty easily. We can check if the left is smaller than there are so many edge cases, man. There are so many edge cases. So we check if, dude, these overlaps will kill me, man. Shit is hard. So, dude, are we even live? Yep, we are live. So, I'm getting confused with the overlaps here. Say that we were here and the segment that we were supposed to jump in also lies within us, right? We are within that segment. So now we need to know if we go here or we go here. This is going to be our edge case. If we lie within that segment already, then we can decide that okay, the next move is going to be what? The next move is going to be to go from here till where, right? So we might be going from here till here, or we might be going from here till here. So if we have to go from to the left after this, so we just jump to the left and then we jump to the left again. And if we have to make a jump again, we have to go right after this, so we'll currently jump to the right and then later we will also jump to the right. And if I was here and I have to jump here, right, and then after that I had to jump here, so I would check, okay, so where are we? We are here. The first thing is that if I ever had to jump here, I would always be here because I'm very smart, because I know my stuff. We can't just waste our moves moving around in here to be at the best place and then we can make a jump, because we only have one turn, right? So we can't forget that as well. I would know where I'm jumping right now. Why? Because I had known since ages that I am going to jump here, and we currently know the direction we are going to jump in. We only need to know the next direction we're going to jump in. So let's say that I knew I had to jump right, all right? So I was going to jump right, and there was an overlap here, right here. So once I make the jump to the right, First of all, the jump currently is going to be to the right, alright? That is something that I know about already. And then secondly, we're also going to know what is the next. Next jump is going to be where. So that is something that we need to calculate. And if the next jump were to be here, then I would have made this. What if this range is very big and I need to jump here next? So if I jump here, then I can make a jump here. Is it possible? It is. However, if I try my very best and jump somewhere here, then I try my very best and jump somewhere here. That actually optimizes the problem. So our next jump is actually going to be right. Or is it? We're complicating the problem a lot. These overlaps will kill me, man. I am slowly losing it. Okay, what if the overlap was at the border? What if the overlap was here? What would we do then? So we have to make the bare minimum. And if we have an overlap, if we have overlap, then we can decide on the go that we are making left or right side there that we are going to, depending on the next place, right? This is very confusing. Very confusing, very confusing. So let's just say that All right, all right, all right. No, we can do that either. We can say. So, God, why it's so hard, man? Why it's so hard? This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite mirror with me now. This is a goal. I have an infinite
Let's
mirror
just
with
ignore
me
this
now.
case for now. Let's just try to.
This is a goal. I have an infinite
Let's
mirror
just
with
ignore
me
this
now.
case for now with general cases and try to.
This is a goal.
So
I
you
have an
see,
infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
So
I
you
have an
see,
infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
So
I
you
have an
see,
infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
So
I
you
have an
see,
infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
So
I
you
have an
see,
infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
So
I
you
have an
see,
infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
So
I
you
have an
see,
infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
Left
I
right,
have an
let's
infinite
just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
Left right, just one.
I
Left
have
right,
an
let's
infinite
just
mirror
ignore
with
this
me now.
case for now with general cases and try to.
This is a goal.
Left right, just one.
I
Left right,
have an infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to. Right off.
This is a goal.
Left right, just one.
I
Left right,
have an infinite
let's just
mirror
ignore
with
this
me now.
case for now with general cases and try to. Right off.
This is a goal.
Left right, just one.
I
Left right,
have an
let's
infinite
just
mirror
ignore
with
this
me now.
case for now with general cases and try to. Right off.
This is a goal.
Left right, just one. Left
I
right,
have an
let's
infinite
just
mirror
ignore
with
this
me
case
now.
for now with general cases and try to. Right off. Left right, just one. Left right, let's just ignore this case for now with general cases and try to. That's right off. Left right, just one. Left right, let's just ignore this case for now with general cases and try to. That's right off. Left right, just one. Left right, let's just ignore this case for now with general cases and try to. That's right off. Left right, just one. Left right, let's just ignore this case for now with general cases and try to. That's right off. Left right, just one. Left right, let's just ignore this case for now with general cases and try to. That's right off. Left right, just one. Left right, let's just ignore this case for now with general cases and try to. That's right off. Left right, just one. Left right, let's just ignore this case for now with general cases and try to. Best right, left, right, when you press it on the from cases and right, best right, left, right, when you press it on the from cases and right, best right, left, right, when you press it on the from cases and right, best right, that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the from cases and right, best that is the case, left, right, when you press it on the cases and right, best that is the case, left, right, when you press it on the cases and right, best that is the case, left, right, when you press it on the cases and right, best that is the case, left, right, when you press it on the cases and right, best that is the case, left,
I'm also suffering with implementation. Implementation should be very straightforward, guys. Being a very I'm also suffering with implementation. Really big implementation should be very straightforward, guys. Being a very implementation should I'm also suffering with implementation. Really big implementation should be very straightforward. I am being a very implementation should I'm also suffering with implementation. Really big implementation should be very straightforward. I mean it is a 400 problem, so I can should I'm also suffering with implementation. It's pretty hard. Really big implementation should be very straightforward. So I mean it is a 400 problem, so I can jump. I'm also suffering with implementation. It's pretty hard. Really big implementation should be very straightforward. So I mean it is a 400 problem, so I can jump. I'm also suffering with implementation. It's pretty hard. Really big implementation should be very straightforward. I mean it is a 400 problem, so I can jump. I'm also suffering with implementation. Here the current is going to get implementation should be very straightforward. I mean it is a 400 problem, so I can jump. I'm also suffering with here the current is going to get systematically wrong right now. I will see or this it is my unit problem, so I can say sure most separate. Here the current is going to get systematically wrong right now. I will see or this it is my unit problem, so I can say sure most separate. Here the current is going to get systematically wrong right now. I will see or this it is my unit problem, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left to the left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most current minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to get left right now. I will see or this it is my unit prime jump, so I can say sure most minus current is going to
Now
It's still bad. It's good now. I'm that was so stupid. How do I do this? I think it's time to see the tutorial, I guess. First, let's note that if we can pass a level with some value of k, then we can make all the same moves and pass it with a larger value. This allows us to use a binary search for the answer. So if we can pass a level with some value of k, alright, then we can make all the same moves and pass it with a larger value. What?
Choco Craze is
Welcome back to another video. This is Code Forces round 9:30 in Div 3. We're gonna solve the fourth problem, that is jumping through segments. Let's see what the problem states. So we have our friend Polycarp here, and he is designing a level for a game, and the level consists of like n segments in a number line. So suppose if this is the number line, there are many segments like this, like this, like this, many segments like that, where ith segment starts at point with coordinate li and ends with ra. Suppose if this is the first segment, it will be L1 R1, and this might be L2 R2 second segment, and third segment it can be on extreme left also. Like, it does not mean that first segment will be, second segment will be after first segment, third segment will be after second segment, nothing like that. It can be very much random on a number line. So this is one idea. Now a player will start the level at point 0, coordinate 0. In one move they can move at any point that is within a distance of no more than k. Suppose if we choose k equal to 5 means he can move a distance of 5 units or 0 units or 3 units. The movement should be at max 5, whatever k he chooses. After their ith move, the player must land within the ith segment, that is at a coordinate x such that it should be part of LR. This means, so after the first move they must be inside the first segment, after the second move they must be inside the second segment, and after the nth move they must be inside the last segment. So if I suppose k equal to 5 means I can take at max 5 units and land at the first segment, then I can take at max 5 units and land at the second segment, then I take at max 5 units to land at the third segment. It may happen that k equal to 5 might not be needed. With k equal to 3 only we can do, or we need k equal to 10, or the k value can be increasing. So again I'm telling, it's not like exactly k value as k. If I tell k value as 5, we can just say that with k value of 3 also you can go, and k value of 2 also you can go to the next segment, but it should not be crossing the k value as 5, that's all. And first move should have the landing position at first segment, and second move should have second segment, and so on. The level is considered completed if the player reaches the nth segment with the rules described above, and they just told this. And Polycarp does not want the level to be easy, so he asks us as usual to determine what is the minimum integer k so that he can complete the level. So why is he asking the minimum integer? Suppose if a number line is having 10 and all the segments are in the range of like 0 to 10, 5 to 8, like that, I can just take k value as 10,000, right? If k value is 10,000, I can just take 0 to 5, whatever k value I can take within the 10,000, so that I can cover the entire 0 to 10 line. So that is not an ideal approach. So they want what is the minimum integer k. That means at least how much k I needed to solve this problem. Now let's see this with the help of an example. Like this is the example here. Let's understand the problem first. So what do I do generally? Like, okay, I need to go ahead and find a k value. So I find k equal to 1, then see whether with k equal to 1 can I move to first segment, second segment, and third segment, like that. With k equal to 2, I try all the possible combinations. Like k equal to 2 can have k equal to 0, 1 and 2. So I take one jump and see whether it's there or not, two moves and see whether it's there or not, like that. Then from the first segment I see with one move can I move to the second segment, or with two moves I can move to the second segment, like that. Then again with k equal to 3 I can again search. If we do like that, according to the constraints of the problem, we will get TLE. So what is the efficient way to do linear search? We will go to binary search approach. So we take a small k value, we have a big k value, and we take the midpoint of that, low and high, we take the midpoint, we assume that is the k value. So if we are able to generate an answer, we decrement the k value. If we are not able to generate the answer, we try to increment it. So low and high, similar to that. So that is the basic idea of that, the outline. So we take small low and big high, and the midpoint is the k value. Based on that, we'll try to find the answer. But the problem here is still not solved. The k value, if I say it's like 5, the jumping can be till 5. So it can be 5 on the left or 5 on the right. So the landing position is what we have to find out. Now, we figured out till this, okay, we are doing binary search only. Now, if the line segment is like this, okay, and suppose I am staying somewhere here, after few jumps I can say that leftmost k value I can have is this, and rightmost k value is this. L of I is this line segment is here, and this line segment is here. Now suppose if I am standing here and I can jump till left k and I can be till right k, is it possible for me to go till Ri? Not possible, right? If this is my exact position where I can move around, I can never be on Ri, right? Because if left k is greater than Ra, this is not gonna work because I tried all my possible combinations, it won't come here. And if suppose left k is here and right k is here, okay, and let's say these are here, there is a gap here. If right k is less than L of I, then also it is not possible. Do I make sense? So that is the first condition we have tried. Right k less than L of I or R of I less than light k. R of I less than left k. If both of them are not possible, we can't land at that particular segment. So if we are not able to land on that particular segment, what do?
I'll review this later. Let's end this for now. I'm so tired. Alright, guys. Bye.